Hi students, this is a video which describes how you will be able to diagonalize a matrix. First, we'll have a theoretical setup by defining what is meant by diagonalizing a matrix. You can see that all the matrices, square matrices, need not be diagonalizable, but there are certain properties which must be satisfied by a square matrix to make it or to convert it into a diagonalized form. Okay, so let's begin the discussion by defining similar matrices. Similar matrices. Two matrices A and B are said to be similar if any one of them, say A, can be written as A is equal to P B P inverse for some invertible square matrix P. So if we can find an invertible square matrix P, and we can write A is equal to P into the second matrix B into P inverse, then we say A and B are similar. Now we can see that this is a notation for writing whether A is similar to B. If A is similar to B, we use this notation. Okay, now we will prove that this relation of similarity is an equivalence relation. That means it's a reflexive relation. A is always related to A because you can have P as I. So A is equal to I into A into I inverse, where I inverse is I itself. Therefore, A is related to A. Now, symmetry, A is related to B will imply B is related to A because A is related to B means this equation is valid for some invertible square matrix P. Now, you take this, you multiply here with P inverse, here with P, so that P and P inverse will be cancelled. There will be B. So I'm writing B as P inverse AP. So it will be P inverse A, P inverse inverse. You will take this as Q, and this will become Q inverse. Therefore, you'll have Q A Q inverse, where Q inverse is Q is P inverse. Therefore, B A is related to B will imply B is related to A. Therefore, it is the relation is, that means the relation of being similar is symmetric. Now, it can be shown to be a transitive relation. If A is related to B and B is related to C, then we can prove that A will be related to C. So, suppose that A is related to B, then this equation is there. Suppose B is related to C, then there is a Q like this. Now we have to show that A is related to C. Now what is A? A here is like this. Instead of B, I can write it as Q, C, Q inverse. Therefore, A into A is equal to P. B, I will be replacing at Q, C, Q inverse. So it will be P, Q, C, Q inverse, P inverse, and regrouping PQ, and this is nothing but PQ inverse. So something is there, PQ, its inverse is there. P and Q are invertible, means PQ also will be invertible with this inverse Q inverse P inverse. Therefore, A is similar to C. Therefore, whenever A is similar to B and B is similar to C, we can see that A is similar to C. Therefore, everything is satisfied by this similarity relationship. Therefore, it is an equivalence relation. Now, a very important result, show that similar matrices have same eigenvalues. That means if two matrices are found to be similar, then they will have the same eigenvalues. Suppose A is similar to B. We have to prove that eigenvalues of A is same as eigenvalues of B. So if A is similar to B, then this equation is okay. You can write as P B P inverse, or P inverse B P. It's because P inverse is P. So we have to show that the eigenvalues of A and B are one and the same. Let lambda be an eigenvalue of B. Therefore, this characteristic equation of B is like this. Now multiply on the left by determinant of P inverse, on the right by P. So you can combine all these determinants into a single determinant. So P inverse BP minus lambda into P inverse IP. Therefore, P inverse IP is nothing but P inverse into I is P inverse. P inverse with P is again I. So this is A. Therefore, determinant of A minus lambda equal to 0. That means lambda is an eigenvalue of A also. Therefore, both A and B have the same eigenvalues. So from this, actually, this problem actually will be getting the property, or we will be getting the concept of diagonalization. So what we mean by diagonalizing a square matrix? A square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Okay, now an important remark. As the eigenvalues of a diagonal matrix are its diagonal elements, and diagonalizable matrix A is similar to a diagonal matrix D with diagonal entries as the eigenvalues of A. That means if A is similar to D, then both A and D will have the same eigenvalues. That means D being diagonal, its eigenvalues are the diagonal elements. Therefore, A is similar to D means eigenvalues of A should come as the diagonal elements of the matrix D. Therefore, D is nothing but a matrix consisting of the diagonal elements as the eigenvalues of A. That's what I mean. So some problems on diagonalization of matrices. So I'll give you some matrices which are diagonalizable. For diagonalizing a matrix, we require some necessary and sufficient condition. But anyhow, for you, you have to see how diagonalizable matrix can be diagonalized to a diagonal matrix by finding the corresponding invertible matrix P. So let's begin by a 2 by 2 matrix. So this is a question: diagonalize the matrix A is equal to matrix 2, 4, 0, 1. You see this is an upper triangular matrix. The eigenvalues are 2 and 1. You need not compute it. The eigenvalues are diagonal elements 2 and 1. So finally, we have to diagonalize this into a matrix with 2, 0, 0, 1. Okay, how it can be done? Here the eigenvalues are 2 and 1. As I have told you, we have to find a P such that A is equal to PD, P inverse. D is nothing but, I told you it is diagonal matrix 2 and 1 with eigenvalues 2 and 1. Now we construct P as follows. See, the construction of P is very important. Find the eigenvectors corresponding to the eigenvalues lambda equal to 2 and lambda equal to 1. So you can see we have done a problem. You have to find out eigenvector corresponding to lambda equal to 2 as x1, x2, and x1 we can take it as 1 and x2 as 0. And eigenvector corresponding to lambda equal to 1 will be minus 4. And once you get eigenvectors, you can create P like this. We can create P like this. So you have to write P as first column as 1, 0, second column as minus 1. So 1, 0, minus 4, 1 will be your eigenvalues. Sorry, P. So P will be 1, 0, minus 4 and 1. So you have to get A like this. 1, 0, 4, 1, 2, 0, 1, 0, 1. So we multiply this one, we just this one, or you can see that AP, you just check, verify it. AP, you can see that this is A into P, you'll be getting like this. PD also will be like this. So one and the same, AP equal to PD means it will be A equal to PD, P inverse. Therefore, A is diagonalized to this diagonal matrix consisting of the eigenvalues. So that's how this 2 by 2 matrix is done. Let us go to a case of 3 by 3 matrix. Here also, for making the problem very simple, I have taken an upper triangle matrix for which the diagonal elements are the eigenvalues 2, 1, 3. So our effort is to diagonalize this matrix to 2, 0, 0, 0, 1, 0, 0, 0, 3. So as eigenvalues are 2, 1, 3. Here the eigenvalues of A are 2, 1, and 3. So we have to find a P such that P into D. D, I told you, this is the diagonal matrix to which this A is similar to that diagonal matrix, P inverse. So how to find P? For finding P, we have to find eigenvectors corresponding to lambda equal to 2, lambda equal to 1, and lambda equal to 3. This is done for you. You have to do it. Actually, it requires some steps. So for eigenvector corresponding to lambda equal to lambda equal to 2 can be taken as 1, 0, 0. And that corresponding to lambda equal to 1 can be taken as minus 1, 4, minus 4, 4, 1, 0, and lambda equal to 3 as 6, 1, 2. So you can write P as first column containing first eigenvector, second column containing second eigenvector, and third column containing third eigenvector. This is your P. Now let us verify whether A equal to PD inverse, PD P inverse. For that, it is enough to compute AP equal to PD. You compute AP, you know A, you know P now, multiply them, you write it as an answer. This is the first answer. Similarly, you find out P into D. So P is here, D you know, P into D compute, you'll be getting another matrix. Second equation from second equation, you have to see whether that is equal to AP is equal to PD. Therefore, from 1 and 2, you have to finally, you will be seeing that they will be same. So A is diagonalizable, which is similar to this diagonal matrix. Okay, that's how diagonalization problems are done. Now, some homework for you to compute. This is diagonalize this matrix. I'll give you the hint as eigenvalues are 0, 3, and 15. This problem we require for the next video. So just compute the eigenvalues first. I have given you the hint. Here the eigenvalues are 0, 3, and 15. Then corresponding eigenvectors are to be found out. P you construct, calculate AP and PD, see whether they are equal. And if AP equal to PD, then A will be equal to PDP inverse. Similarly, another problem, a 2 by 2 matrix. Here the eigenvalues can be found to be 2n minus 2. Corresponding to n minus 2, you have to find the eigenvectors. Using eigenvectors, you create P, then check whether AP equal to PD, where D is nothing but the diagonal matrix 2, 0, 0, minus 2. Okay, so with that, we end this video on diagonalization of matrices. Thank you for watching. In the next video, we will learn how you can deal with what is that, quadratic forms and that canonical form of quadratic forms using diagonalization of matrices. Thank you very much for watching this video.